ठीक है।
Start.
Good afternoon, everyone. I am Mudasir. So today I'll be talking about machine learning and determination, membership determination of star clusters. I'm sorry, I will be a bit faster because I have to rush. So all of you must be knowing what is a star cluster basically. So star cluster is a group of stars which are born from the same molecular cloud. So why do we study star clusters? Basically, we study star clusters because they are the building blocks of our galaxies, and we understand the formation and evolution of galaxies. This is very essential to even understand the star cluster populations like young associations, open clusters, old neighborhood clusters. So membership determination is a very important problem. It's a very crucial problem in star clusters. Earlier, we used to get special location. Then we used to use color magnitude diagram to study it. But now we can use vector point velocity as well as parallax proper motions to study this problem. So whenever you study something or whenever you compare something, you always had a wish thing should be like this and that. So in case of studying star clusters, the wish list is like, we need to have a high precision astrometric data with positions, parallax, and proper motions, which are of great importance in studying the studies of star clusters. So this wish was fulfilled by Gaia. So Gaia is basically an European Space Agency satellite, which was launched almost 10 years ago in 2013, December 2013, which is already there on extension now. So it has studied, it will study almost 1 billion of stars. So Gaia helped us, since because of Gaia, astronomy shifted from data poor to data rich science. So we have a huge amount of data, and in order to study that data, we need something special to do that. So this is the point where machine learning will help us. So machine learning helps us to study these big chunks of data which we have from Gaia or other SDSS, SIMBAD, etc. So machine learning is basically of three types: supervised, unsupervised, and reinforcement learning. So we used supervised as well as unsupervised. In case of supervised machine learning, we used a technique called random forest. So in case of random forest, we use, since in case of supervised machine learning, you need to have a training data. So in order to have a training data, we used Candid Gauden's 2018 paper as a training data set. And then we extracted our sample. This is the picture of that paper. And this is our sample. This is a cluster group of 9 clusters, which we extracted from that paper as our training set. So then we applied random forest, and this is the paper that got published. This is our work which we did. And these are the plots. These are sky plots, and these are proper motion and parallax plots. Blue ones are ours, orange are from the Candid Gauden, and the green one is basically a combination of both. So we can see, since you can see from those plots, blue plots, they're a bit wider because we took radius double the Candid, because we didn't want to miss any stars or outliers, etc. So we doubled the radius which they had taken. So these are the color magnitude diagrams. Orange ones are theirs and blue ones are ours. So you can see that blue is slightly better because we have, the number has increased because we use double the radius. This is the validation, since we divided the training set into 30 to 70. And once the validation is done, the training testing is done, then we did a precision. If you see here, precision is 86%, 93%, 88%, etc. Precision basically gives you an idea that how many members we extracted back when we did this random forest thing, because we almost got 86%, almost 90% of members we got back while running this training data set. So these are the results from random forest. It's a supervised technique. The membership has increased almost 2 times, and the sizes are revised. Like cluster members, even we have discovered the escape numbers or outliers. Since in case of supervised machine learning, one thing is very important, that is the training data set. So if your training data set is bad, you will get the bad results. If your training data set is good, you will get the good results. So that's why here comes another thing that's called unsupervised machine learning. Since in case of unsupervised machine learning, you don't need to have any labeled data. So in case of unsupervised machine, there are 2 methods which we have used. One is GMM, Gaussian mixture model, and another one is DB scan, density-based spatial clustering analysis with noise. So in case of GMM, GAU 2018 has used the DB scan, and Manan Agarwal 2020, they have used the GMM. So we studied both these papers and tried to find out how can we do this. So this is the Gaussian mixture model. In case of Gaussian mixture model, we all know that mean is kind of a center and covariance is kind of a width. So we Basically, in case of Gaussian mixture model, this is like a probabilistic approach using density to find the clusters. So these are our results. This is for M67. These are the members we got for different clusters. And then comes DB scan. In case of DB scan, we also choose a search radius 0.5 for distant clusters and 1 degree for the closer clusters. And I hope this will run. Is it? Yeah. So in case of DB scan, there are two important parameters. One is epsilon and the second one is minimum points. So epsilon is kind of a radius and minimum points is the number of points you want to have in a cluster. So in case of, if you see, look at this, what if, for example, in this case, the minimum points is 4. So if there are 4 points around the center of a point, then we can say these are the members. That point is the core point. So a core point is a point around which we'll have at least the minimum number of points around that class, around that point. So then is the border point. In case of border point is there are also members in the region of that, but they are not exactly the number of minimum points. So it can be less than a minimum point. So that's called a border point. And the third one is called outlier or noise. So it is outside this. If you see, this point is a noise as of now. So this is a cluster, because if you see that, look at this, it has 4 points around the central point. So this is how DB scan works. So these are two important parameters which you need in DB scan. One is epsilon and the second one is minimum points. So this is when we ran DB scan on NGC 2682, that's M67. So these are the predicted members and the canted members. Canted members are orange and the green ones are obtained from the DB scan. So if you see, even when we ran it with the GMM, and this is both are the same clusters. It's 2682 for both the methods, GMM as well as DB scan. So almost EVC CMDs are almost similar. So that means we can say they agreed upon each other to a very large extent. These are the results for the 9 clusters which we calculated. And we also ran Astica, which is basically a code which gives you, it's a package which gives you the stellar parameters. Even in case of running DB scan, we could also see that membership has increased. Even in some cases, it was up to 4 times. The size of studied clusters also increased with the increase in membership, and we can study outer regions of clusters. Since we have not used photometric data while estimating the membership, we can identify variables, pre-main sequence stars, as well as other possible non-main sequence members of the clusters. Thank you. I'm sorry for being fast because I had to rush. Thank you.
Thanks.
Should I?
Yeah, you can take it next.
So you did this machine, right? So you pull the DB scan on supervisor using the random forest.
Yes. No.
So random forest was
Random
What are you using? PPT?
Yes.
Just put whole desktop. Achha. You want to use your desktop only? Achha, you have a PPT. Okay. Sure. One slide from it. Next slide.
Good afternoon. I'm Somnath Das from University of Hyderabad. I'm working under Professor Suresh PK there. So I'll talk a little bit about the kind of Python codes we have been doing in our lab. So the theme of our work is about cosmic inflation. So in cosmic inflation, I'll not go into too much detail about the physics. These are a few parameters that we usually use. So this epsilon and eta, we take various epsilon and eta. Epsilon and eta, they will vary for various models. And then using various algebraic combinations of them, we get various observables that various observation groups are measuring. So usually people are concerned with the type of potential structure that is there. So we are also trying to deal with that. And based on that, there are hundreds of models available. And it is quite the calculation to get a plot like that. It takes some time, like for people to do by hand. So till now, people have been doing it by hand. I'll just briefly tell what this is. This is like there are two inflationary parameters, R and NS. R is the tensor to scalar ratio, which has something to do with primordial gravitational waves, and NS is spectral index, scalar spectral index. So from the observational data, we can plot contours like that, and for the individual models, we take data point. So here it's a single field model. It is chi-square model. We can see it is going outside data points, and accordingly we can draw inferences out of it. So the thing we did was for a specific V, one needs to calculate all these inflationary parameters and then plot it in the context of the latest data. So what we did was we wrote a code which allows user to input the potential as a function of phi, and the code is also able to handle coefficients if we want. So it can handle any number of coefficients. So we can make a nice functional form, whatever functional form the potential is in. So the user gets diverse set of options to deal with. So these are the modules that we used. This is NumPy. It is for handling numerical operations and data manipulation. Matplotlib, we have seen it here already. Matplotlib is for visualization of data, and also we can create contour plots with Matplotlib. Then I have used SymPy so using SymPy, one can take derivatives of various functions, and in Python, even if you input a function which has variables, SymPy is able to handle those things. And tkinter and tkinter's message box, these are for user interface. So this is just for the graphical interface thing. Now the main function we have is generate plot. So here our purpose is to do a cosmological parameter plot in the context of contours, and this is the basic algorithm that we are doing. We retrieve the potential function from GUI, including the coefficients and all these things, and then we do differentiation on that and arrange the parameters according to inflationary parameters, and then plot the contour data. So this is just GUI overview. Skip that. So how the code runs is that when I'm sorry, I cannot show the code due to obvious reason. So how the code runs is that when we execute the code, it asks for how many coefficients we need, and I have given input of 2. So based on that, it opens a window like this. So here you can see one can give input of V of phi. Phi is the scalar field that is driving inflation. So let's consider it as some variable X or something. So with a variable and with 2 coefficients, we can input, and we have to give an initial phi value, which is related to the physics of inflation. So after inputting, if we click on generate plot, it gives us tensor to scalar ratio, spectral index, and it also gives the plot according in the context of the latest data. So it at least saves a few days worth of time for anyone who is doing inflationary cosmology. And so our model, like the Python code that we wrote, it will be helpful for people, not only for people who are doing inflationary cosmology, but if we see this thing. So after inflation, it is followed by reheating, and then there are particle production and all those kinds of interesting physics happen. So based on inflationary potential, if one wants to extend it to later physics, then this can be a good software to use. I want to. Huh? I'm just in like in the middle of my pitch. I want to thank Manu, Ayuka, and all other organizers of EDIP 23 for allowing me to share my work. And I want to thank University of Hyderabad for facilitating. And I want to thank Government of India for funding my project. Thank you. Any questions?
Why you want Zoom? And speak into that thing. Keep the mic. And I've given you permissions. Okay. Yeah, you are co-host. So
Okay.
first, introduce yourself. Your
Yeah,
name.
yeah, definitely. Very good afternoon to everyone. I'm Shanmukh. I'm from Osmania University. I finished my master's in astrophysics this academic year. So as a part of my master project, I have worked on mass estimation of active galactic nucleus that are most massive, and I have used SDSS data to estimate those masses. So firstly, to understand what are actually agents. So to briefly classify agents, agents are actually classified into 2, whether they can be in radio quiet or radio loud. So when we talk about radio quiet and radio loud doesn't, it just means that it actually emits a lot in radio spectrum. So the ones that since SDSS is a visible telescope, I have used my sources is a QSO, which is a quasi-stellar object. So based on the inclination of the galaxy, basically active galactic nuclei are the supermassive black holes that are sitting at the center of the galaxies. So anyways, there are again two types of galactic nuclei, which is an active galactic and an inactive galactic nuclei. Like we have at the center of the Milky Way, which is an inactive galactic nuclei. Okay, so for an active galactic nuclei, based on the inclination of how we observe, it is again classified in two, which is type 1 AGN and type 2 AGN. So we'll be talking about those agents that are whose center is directly coming to whose center is visible to the telescope that we are observing, so that we can easily get what is happening in the center of a galaxy. Okay, so why do we need to have a mass estimation? Like what is the importance? Because in astrophysical sense, when we talk about data analysis of things of astrophysical objects, mass estimation is very important for like any other object, not just about black holes or something. So coming to the black holes, mass estimation is important in this sense is we can understand the bulge dynamics, we can understand the accretion disk, how it behaves. We can also have various relations between radius and luminosity, and we can understand the relation between each feature of an AGN, what we see in the spectrum that we get. So as SDSS sees both spectrums and also photometry does both, I have used SDSS spectrums of a quasar. So this is the SDSS spectrum. This is the SDSS telescope. So why did I use? Because I'm talking about agents which are more massive. When I say that it is more massive, it means that they are very far away and they are like almost at the age, like as I'm saying, it is galaxy in the center of a galaxy. They are very old, right? It should be very old black holes. So for old black holes, the redshifts are very higher because the galaxies are too far. The redshifts are too high. So for too high galaxies, we need to have a high resolution spectra. So for high resolution spectra, SDSS gives a very good high resolution spectra because it has 1,000 fibers. You can see the aluminum plate that is there. It has 1,000 fibers, and each fiber dot, it observes 1,000 agents at one time. That is a benefit that we have from SDSS. Hence, I use SDSS data to analyze my agents and find out mass out of it. So as I said, like SDSS have a lot of surveys, just like BOSS, and recently in the first class we have seen that there is also manga, right? It is also from SDSS survey. So these are all the other things that SDSS does apart from BOSS. So before going to mass estimations and all, I'll briefly say like how to know the notation of a spectrum, like what do we understand from a spectrum if we get a spectrum out of a telescope. Okay, so we have a lot of emission lines, right? Emission lines in the sense, if we have a cloud or something that is obstructing the radiation, so we get the emission lines that is based on the property of the gas cloud that is there. So we have a lot of other emission lines. So based on the wavelength that it is emitting, we have different kinds of emission lines. Like we have in the visible spectrum, we have H beta and H alpha. H beta itself are nothing but like from the higher to the first state, it is like H alpha. When you say H beta, it is from next higher state to the first state. It is just that. It is just a notation we need to understand when we use a spectrum. Okay. So these are my samples that I have chosen to estimate mass. So you can see, but as I'm speaking, as I said that H alpha and H beta lines are in the visible spectrum, but none of H beta and H alpha lines are there in this spectrum actually. That is because if you can see like, if you can see the redshifts are around 3.5 because it is highly redshifted. Almost even the data that we're getting in the visible, when we correct for redshift, it will be going into the UV band or X-ray band. I'll be showing in a while that one also. So for this one, we have Lyman alpha line and C4 and all these prominent lines. So how do we choose a spectrum like to analyze? So when you want to analyze and estimate mass out of any spectrum, you need to have a spectrum such that it is very clean, and you need not do so many corrections, so that you won't have a significant error bar at the end when you want to estimate mass. Because there are various techniques to estimate mass, and one of which is famous is reverbation mapping. It is very important and very much popular. People will be using. So, but the problem, because I didn't use reverberation mapping because I'm talking about high redshift quasars because they are very distant. So what happens in a reverberation mapping technique is that I should be continuously seeing the AGN and getting data from that. That doesn't happen for high redshift quasars because they are too far away and we cannot have a high resolution data from that. So instead of doing a reverberation mapping, we go for a normal mass estimation based on the virial, that is called virial mass estimation. I'll come to that. I'll be showing. So for that, before we go into getting the conclusions of how do we estimate mass, we need to do a lot of spectral corrections for that. So for that, firstly, what SDSS suggests, what are the spectral caveats that SDSS suggests based on the data that it retrieved from is very important. So first one is that everything that SDSS get is based on the vacuum wavelength, right? But we are observing in the air wavelength and we want every flux in terms of air. So we need to convert vacuum wavelength into air wavelength. So that is the first correction that I have done. And after that, since it is far away from that, there is a galactic reddening happening also. So I need to correct for galactic reddening where the flux, there is a lot of flux difference also. But if you can see, there are actually two different lines in that. If you can see the legend, there is vacuum wavelength and air wavelength. The dotted lines are air wavelength. There is like very minute difference, but that also accounts a lot when we are estimating in the final one. That accounts a lot. It contributes a lot. So every precise correction is very important when we are doing a spectral correction. So as I'm speaking about galactic reddening, so the green one shows the corrected one because the flux has just shifted to upwards in the graph, because the flux that we are getting from galactic because of galactic reddening is reduced because the radiation that we are getting is absorbed a bit by the dust that is there in the interstellar medium that we are taking into consideration. So the next correction that I've done is a redshift correction. As I was speaking, since the galaxies are too far away and moving away from us, we need to correct for redshift. As I said, my redshift is 3.5. When I say redshift is correct, when I want to correct a redshift, I mean that I'm correcting the wavelength as well as flux, because when the galaxy is moving away from us, in the sense of Doppler effect, which is much more analogous when I talk about redshift. So since it is moving away from us, we need to understand that the wavelength and flux both will be altered. So when I'm correcting for redshift, the pink one that is there on the left side, that is the original spectrum that I've got as a high resolution spectrum. But when I'm correcting it, it is corrected to the green one. That means it is completely shifted to the UV band, because the pink one is around from 4,000 to like around 10,000, which is in the visible region. But the one that I have after correction, it went to 800 to 2,000. So that much the redshift has altered the spectrum. Anyhow, it doesn't matter because it only matters when we want to understand the emission lines. So when I take it is a normal, only the x-axis values changes. That's it. Nothing else changes. But the important thing is that, as I've shown, the emission lines are important. So the emission lines that are there, like Lyman alpha, carbon 4, all these are very important. And based on emission lines, we can understand, because every emission line has its own corresponding wavelength, by which we can understand that redshift will be accounting to that part of the electromagnetic spectrum. So after these things, what I've done is that actually to estimate mass, we have to pseudo continuum fit the complete spectrum. But since I have to fit the continuum spectrum for all those, I have a Lyman alpha forest, and since this is a very high redshift quasar, I cannot pseudo continuum fit everything, because pseudo continuum fit adds this Balmer line fitting and all those things. But I don't have any H beta lines in this. And for every emission line, there are like very prominent absorption lines. So instead of fitting the whole spectra, based on the mass that I'm estimating for one emission line, I just selected carbon 4 as my emission lines from which I'll be estimating the mass. So I've selected this part of the emission line in the spectrum, and then I have chosen a continuum window, of which I have fitted a polynomial, and I have just normalized such that the whole emission line comes to the origin, such that I can eventually find the full width and half maximum of the emission line. I'll come to that why I'm doing that. So why do I have to do the continuum subtraction? So what is a continuum? Continuum is like when you theoretically understand what is an AGN, you won't have these emission lines. You just have a, when you think of a black body, it is just a small line, right? But, okay. So when you talk about a continuum, it is, when you theoretically understand a continuum, it is like a continuous spectra. You don't find any absorption in these things. So you need to firstly remove that part. Only then you can have the pure emission part from which you can estimate what all features you want to do. So I have subtracted the continuum such that it got normalized. Now I can fit the Gaussian and find the full width and half maximum from that. So we cannot fit a single Gaussian. That is because the emission lines are broad. So this broadening of emission lines is because of some effect called Doppler broadening. So why does this Doppler broadening happen is that I'm talking about an AGN. So how is the structure of an AGN? I'll go to the first slide once. So the structure of an AGN, there is a supermassive black hole sitting in the center, and there is an accretion disk around it. After that, there is a fast moving clouds around it that is called broadline region, and there is a huge obscuring torus around it that is like a donut that you can see there. So because of which we can estimate the velocity of that broadline region and connect it to the mass. So since this accretion disk and torus, they are all agreeing to the fact that they will be following Keplerian laws, it is just a Keplerian disk. So I can apply all the Keplerian laws like V equal to under root gm by r, from which I can estimate mass directly. It is not that simple, but the overall theory is that one. So for that purpose, I need to find the FWHM, and FWHM gives us the velocity. So if you can remember the Keplerian velocity formula, which is V equal to under root gm by r, I got V. What is the velocity? I need to get the radius of the broadline region. Okay, so for radius of the broadline region, it is directly connected to the luminosity. What I have to do now is that I have to completely change the flux that I've got from the spectra. I have completely changed into the luminosity versus wavelength. So as we know, luminosity is flux into area. I can completely change the flux values into luminosity values and get luminosity value out of it. Since I'm working with carbon-4, there is a relation for black hole mass estimation for carbon-4, which relates to the luminosity class at 1350 angstroms. So the luminosity peak value at 1350 angstrom corresponds to the radius of the broadline region. So after getting these values, I've substituted in the mass formula that is there, F into R. This is the same thing, V equal to under root gm by r. I've just rearranged the terms to get this one. So just substitute all the values that you have got, and I have finally estimated the black hole mass to be around 0.5 billion solar mass. So which is almost near to the values that is there in the literature. So, but I couldn't get the exact value. That is because I couldn't do the pseudo continuum fit, and there are also a few other spectral corrections that I have skipped because my sample that I have chosen has a lot of absorption lines in the emission lines also. So to have a simple thing, I have made things simpler, but still I haven't had a huge significant difference. It was mostly near. So that is all about these things. Thank you. Any questions, please?
Yeah.
So you worked on quasars, right?
Yes.
So like secret and quasars are more or less.
I worked on QSOs. Quasars and QSOs are different. Quasars are quasi-stellar radio AGNs. QSOs are just like that is radio. This is like just only visible ones.
Like secrets are also radio point. And
Yeah.
you mentioned about the broadline region.
Yes.
Could you tell something about your observations regarding the line flux from the, like how is the fluctuation of the line flux from the broadline?
Okay, so you're talking about this emission line.
Yes. Could you just
Like I didn't understand the line that word terminology.
thank you.
Mm.
So could you like if you have observed flux from that particular part?
Yeah, the flux that we'll be receiving, it is from the broadline region completely. So all the emission lines that we are getting, because there is a torus around it and there are fast moving clouds around the broadline region, we are getting all these emission lines. It means because from the emission lines that we are seeing in the spectra, we can infer that the broadline region has these elemental compositions, like all these Lyman alpha. Lyman alpha is hydrogen line, right?
That is what I was thinking. Have you seen any sort of declination in the like over the time?
No, I didn't do any over the time observations. This is a single epoch observation. So as I said, sorry, thank you for this telling me. So this is, as I said, if you're talking about reverbation mapping technique, then I'll have a over the period observations. For this one, this is like a single epoch observation. So you get a spectra out of one optical fiber for a specific time. That's it. It is just a normal observation. No, F is a virial factor. Virial factor, like I'm talking about the distribution of gas. If the distribution of a gas is spherical, then F value will be 0.75. So for a different distribution of gas molecules, we'll have a different F value. So to understand, like to take it more in a simpler way, we assume a spherical distribution, for which I took F value as a 0.75. F is a virial factor. Okay, so for continuum subtraction, what I've used is that, as I said, for continuum subtraction, I just took the window. As I mentioned, 1450 to 1460 and 1600 to 1610. That is the wavelength values that are there. Just, if you can see my cursor, there is a flat region here. There are no absorption lines here. And there are no absorption lines here also. So I just took those two lines and I removed the emission part completely. So if you can imagine, I have few dots here, I have few dots here. Okay, I have just fitted a polynomial such that it will go as a straight line from here. I could have fitted some other power law also, but polynomial is much more easier for me. So it was just like a straight line. And I removed the straight line from that so that it will become normalized. Python. I did everything in Python only.
The homomorphic extent that you have defined, the last slide, which cosmological model are you using?
For
D equal to
that one, sir.
calculation, but eventually you must-
Okay, I forgot. So what is happening here is that when I'm changing it, like in the flux formula, we have F equal to 4 pi d square, right? D is a distance from here to there. I need to go. So there is a cosmological calculator given by that UCLA. So if I give the RA deck of my source, I'll be getting the distance.
But it will be taking some value of the matter density background.
Yeah. It took a Hubble parameter H naught value by default. It has a default one. Default value, yes.
Simple lambda scale.
Yes. Yeah. If you want, I can once check in the website and tell the value.
The default ones are there.
Yeah.
But others you can change it if you want.
I can change it also. It is I didn't do.
That's right.
Yeah.
Any more questions? Everybody's hungry?
Yes.
Because it's 53. Two more people have to present. He and this thing. We can do that after lunch if people are hungry. So let's go for lunch. Is that fine?
Yes.
Or you want to sit hungry? You want to go? Okay. So we come back and yours will happen. Don't worry. He and yeah. Two people. After. Sorry? No problem.